What specific problem does the proposed method aim to solve?
The proposed method aims to solve the problem of assessing the trustworthiness of responses generated by large language models, LLMs, in real time without the need for independent research or cross-checking. The method introduces a trustworthiness score, denoted as gamma, based on the concept of harmonic robustness, which measures the stability and explainability of LLM responses. By measuring gamma across various queries in popular LLMs, the method quantitatively ranks the reliability of these models in different domains, such as Web QA, Truthful QA, and Programming QA. The goal is to provide users with a metric that indicates whether they can trust the response generated by an LLM, ultimately reducing the burden on users to verify the accuracy of the information provided by these models.
How does the proposed method or algorithm work? Illustrate step by step.
The proposed method works by measuring the robustness of large language models, LLMs, through a metric called gamma. This metric is based on the concept of harmonic robustness, which evaluates how close a machine learning function is to being harmonic, indicating stability and explainability. The algorithm involves forming a ball of input in word space, sending these inputs through the LLM to get outputs, and then calculating the angle between the average ball output embedding and the original output embedding. This angle, or rather the sign of the angle, represents the gamma value. The implementation of the algorithm involves choosing an embedding for converting textual outputs to vectors, such as the industry standard ADA002. The ballpoint's functional approximation is created by appending random ASCII control characters to the input string to provide a sufficient ball approximation. By generating perturbations of the input string with random characters, the algorithm measures the stability of the LLM output to these perturbations. The gamma metric is then used to assess the trustworthiness of LLM responses. A low gamma value, close to 0, indicates stable and trustworthy responses, while higher gamma values signify instability and potential hallucination in the LLM output. By analyzing the gamma values across different popular LLMs and domains, the algorithm correlates gamma with trustworthiness through human annotation experiments. The results show that LLMs with low gamma values are generally more trustworthy, while higher gamma values may indicate less reliable responses. Additionally, the algorithm can be used to efficiently find adversarial prompts by following the gradient of gamma, which tends to lead to higher frequency of adversarial examples.
What are the theoretical or practical benefits of using this method?
The theoretical benefits of using the method of harmonic robustness, specifically measuring the unharmonicity, gamma, in large language models, LLMs, lie in providing a quantitative metric for assessing the trustworthiness of LLM responses. By evaluating how close an LLM function is to being harmonic, which signifies stability and explainability, gamma offers a standardized measure of robustness in feature space. This allows for the identification of points where the model's output may not be trustworthy, aiding in flagging potential false or misleading answers. Additionally, the method provides a way to gauge the reliability of LLMs across different objective domains, such as Web QA, Truthful QA, and Programming QA, enabling users to make more informed decisions about accepting LLM responses without the need for extensive manual verification. Practically, the method of harmonic robustness offers a model-agnostic and unsupervised approach to measuring the robustness of any black box LLM in real time. This means that it can be applied to a wide range of LLMs, including popular models like GPT-4, ChatGPT, and Smaug 72b, without requiring access to internal model parameters or training data. By utilizing gamma to estimate the likelihood of wrong or hallucinatory answers automatically, users can quantitatively rank the reliability of different LLMs, helping them choose models that exhibit higher trustworthiness scores. Moreover, the method's ability to stochastically follow the gradient of gamma in stochastic gradient ascent can efficiently expose adversarial prompts, providing a tool for detecting and mitigating potential vulnerabilities in LLM responses.
How is the method validated or tested?
The method is validated or tested through human annotation experiments to show the positive correlation of gamma with false or misleading answers. The study demonstrates that following the gradient of gamma in stochastic gradient ascent efficiently exposes adversarial prompts. By measuring gamma across thousands of queries in popular LLMs and conducting experiments in various objective domains, such as Web QA, Truthful QA, and Programming QA, the researchers were able to estimate the likelihood of wrong or hallucinatory answers, automatically and quantitatively rank the reliability of these models. The validation process involved sampling 100 questions from each model applied to each corpus, and asking a team of unbiased annotators to evaluate the trustworthiness and relevance of the answers from the LLMs. The results were consistent, with annotators typically differing by much less than a point on any given answer, indicating reliable inter-annotator agreement. Additionally, the study computed Fleisch kappa at about 0.6 for all three domains, further confirming the consistency of the validation process. The method's effectiveness in measuring trustworthiness was demonstrated through the correlation of gamma with the quality of responses across different LLM models and domains, showcasing how harmonic gamma to 0 LLMs are generally trustworthy, while higher gamma values may indicate instability or lack of trustworthiness.
What results were achieved with this new method?
The new method achieved results in measuring the trustworthiness of large language models, LLMs, by introducing the concept of harmonic robustness, specifically through the metric gamma. By measuring the unharmonicity of LLM outputs, the method was able to quantitatively rank the reliability of various LLM models across different domains, such as Web QA, Truthful QA, and Programming QA. The study found that LLMs with low gamma values, such as GPT-4, ChatGPT, and Smaug72b, were more trustworthy in their responses. The method correlated gamma with trustworthiness through human annotation experiments, showing that stable answers with gamma close to 0 were generally reliable. The study also demonstrated that following the gradient of gamma could efficiently expose adversarial prompts, providing a way to find misleading or false information generated by LLMs. Additionally, the method allowed for the automated measurement of LLM trustworthiness without the need for ground truth answers, showcasing its unsupervised power in evaluating LLM performance. Overall, the method provided a novel approach to assessing the robustness and reliability of LLM responses in real time, offering a valuable tool for users to gauge the trustworthiness of LLM outputs.
What are the limitations or drawbacks of the method?
The limitations or drawbacks of the method outlined in the paper include the need to reduce temperature fluctuations in LLMs to a benign level or eliminate them altogether, focusing on t=0. Additionally, when directly accessing the input layer of the LLM is not possible, as is the case with commercial black box models, the method is restricted to using string inputs, which may limit the effectiveness of perturbations in token embedding space. Another limitation is the reliance on adding random non-printing ASCII control characters to the input string to measure stability, which may not fully capture semantic variations in the LLM's responses. Furthermore, the method's interpretation of trustworthiness based on the harmonic condition may not always align with the actual correctness or quality of the LLM's outputs, especially in the realm of natural language processing where semantic variations can exist. Lastly, the method's effectiveness in measuring trustworthiness may vary across different LLM models and domains, and it may not fully capture the nuances of trustworthiness in all scenarios, such as when dealing with coding type questions where a single typo can lead to failure.